Tech topical, text best talk show. Tech topical, tell me what's the topic, yo. Tech topical, talk tech topic show. Tech to the topical. Tech topical, text best talk show. Tech topical, tell me what the topic, yo. Tech topical, talk tech topic show. Tech to the topical. Tech topical, text best talk show. Tech topical, text best talk show. Tech topical, tell me what the topic, yo. Tech topical, the topic is technical. Tech topical, the topic best talk show. The tech topic to the topic. Tech topical, the text best talk show. Tech topical, talk tech topic show. Tech topical, the text best talk show. A tech topical, tell me what's the topic, yo. Tech topical, talk tech talk show. A tech to the topical. Tech topical, text best talk show. A tech topical, tell me what's the topic, yo. Tech topical, talk tech talk show. A tech to the topical. Tech topical, text best talk show. A tech topical, tell me what's the topic, yo. Tech topical, talk tech talk show. A tech to the topical. Tech topical, text best talk show. A tech topical, Brian Ross in the host. A tech topical, tell me what's the topic, yo. A tech to the topical. Tech topical, the text best talk show. Tech topical, don't you forget it, yo. A tech topical, talk tech topic show. A tech topical, the text best talking show. Tech topical, text best talk show. Tech topical, tell me what's the topic, yo. Tech topical, talk tech topic show. Tech to the topical. Tech topical, text best talk show. Tech topical, tell me. Nice. I love seeing my face on the screen. Hello, everyone, and welcome to Tech Topical, Tech's Best Talking Show. Today, of all days, it is a very special day, and we will talk about why perhaps maybe later. But of course, every Tech Topical day is my favorite day of the week, and that is because today we are going to be going over quantum computing for the rest of us. Because for the longest time, only the physicists and only the scientists were able to understand quantum computing. They were the only ones who got to play with it. But now you, viewer, and me, talker, and Elias are going to be learning a little bit about quantum computing and maybe how we could actually use it. Because that's the thing with a lot of these theoretical physics, fun time concepts, is that, you know, they tell you all this stuff and then you don't know what to do with it. You don't know, you can't, can I build something with this? What do I do with this? And so that's what we're going to be learning here today. We're going to be learning from the best in the biz. We're going to be learning from Microsoft. And to be honest, I think I'm going to make a prediction that 90% of this is going to go over my head. See, we just don't know, but maybe not. I think I'm going to have a little bit of help here today because I have computer science whiz and the number one high schooler that I know of that can talk about this stuff, and that is Elias Wambugu. Thank you for coming again, Elias. A Tech Topical favorite.
Being, the favorite guest on the show, I don't know if I could hold up to the expectations of being the best high schooler, when it comes to
that
computer
I know
science. Okay, if it's that then yeah, I can do that for sure.
Yeah, that I know of, because I don't know that many high schoolers. But yeah, no, for sure. Out of all five of them, dude, you're like number one for sure. Like not even close to. So yeah, that's
respect.
For sure. You put that endorsement on your LinkedIn. So
exactly.
Here's what we got going on today. So there's this very interesting talk given by Microsoft Research, and let's see what the description is. So now we'll all know exactly what we're getting into. But this talk discards hand-wavy pop science metaphors and answers a simple question from a computer science perspective. How can a quantum computer outperform a classical computer? That's the same question I had about quantum computers. I think it's the same question everyone has. So we're going to learn the following. We're going to learn representing computation. Okay, representing computation with basic linear algebra like matrices and vectors. I kind of do you know any linear al, Elias?
I tried to grasp it, but not as much.
Yeah, I know a little bit of it. I know what
Yeah.
I know what a vector. I know matrices of vector. If it's basic, maybe we'll get lucky and understand some of it. And we'll also learn the computational workings of qubits, superposition, and quantum logic gates. I'm sure we'll learn what all of that means. Solving the Dutch oracle problem, the simplest problem where quantum computer outperforms classical methods. They say outperforms in the present tense, so I guess it exists now. That'd be safe to say, right? That's like my crossword
Yeah.
puzzle muscle memory coming in. Bonus topic. Oh, there's bonus topics. Quantum entanglement and teleportation. Oh, this is going to be a crazy talk. Okay. This
All right.
talk concludes with a live demonstration of quantum entanglement on a real world quantum computer and a demo of the Dutch oracle problem implemented in Q# with them. All right, let's just go ahead and dive right into it and see what happens.
This
All
most
right.
romantic of all subjects. Quantum
Are you a big, yeah, I'll leave the subtitles on.
Yeah.
All right, I'll leave subtitles on. Should I full screen it? See how
Go
it
for
looks.
it.
This is a talk aimed at computer scientists. We will not go over very much, if any, physics during this talk. We won't go over like the double slit experiment or uncertainty principle. We're not learning about any of that. This is
Okay, no physics during this talk. No
Okay,
double slit experiment. No
Okay, good.
the other one. And should I talk about what the double slit experiment is? You know what that is.
No, I don't actually.
It's this famous physics problem where if I have a piece of paper and there's like, it's kind of hard to explain accurately.
you
And I'm gonna
fold
get it
it?
wrong.
Like if you kind of like go like this, or like is- okay, so it's basically like it's a faster way to travel through time, if I'm not wrong.
Oh yeah, I think that's the like the wormhole type of thing with special
Okay,
relativity with the gravity and all
okay.
that. Yeah, I know what you're
Yeah.
talking about. This
Okay.
is the one. This is close. This is the one where it's like if you have a piece of paper and there's like light beaming at it, a particle can be on either side or it is on both sides depending on like your observation. Because with
Mhm.
quantum stuff, like if you observe something, then that changes it, which is why
Yeah.
it's quantum. So the double slit experiment is showing like how something can be on like both sides at once. It gets kind of complicated, but anyway, we're not learning any of that.
Okay, good.
Yeah. So don't worry about it. Yeah, Schrodinger's cat. You know that one?
Nope. I don't know that many theories. That's
The cat
thing.
is alive and dead. All right, last thing, and then this will be the last physics. So there's a box because a
Okay.
lot of people probably don't know this. So there's a
Mhm.
box and there's like poisoned food inside of the box. I don't know why this is
Okay.
the example, but then you put a cat in the box and then you put you have the box over the cat and the food, and the question is the cat alive or dead? And the answer is we don't know, and it can be both because of
Yeah.
quantum uncertainty. And the only
Mhm.
the only way we can know is if we observe it. But if we observe it, then we're actually changing the outcome in some sort of sense. It's like a poor
Oh.
explanation of it. Have you?
Okay.
Does that ring
I
any
think I
bells?
know because I was watching Silicon Valley, and
Yeah.
they use an example of the bird egg. Like if you call if the one of the characters had called the I don't know what it was, but if they had called the facility, then that would have proved that the egg is dead. But if he doesn't,
Yes.
if he doesn't call it, then the egg is alive. So it's like, yeah, no, I get what you're saying now. I get it. It's a weird example, but I get it.
Mhm. I remember
Yeah.
that episode too. All right, so we're not doing any of that.
Okay,
Here we go.
that's good.
I'm going to stop
We'll
it a
come
lot
up with a
too.
computational model, which you will all find it fairly intuitive, I think. Use a state machine.
Okay.
And we will run a quantum algorithm on it, show that it outperforms a classical computation model, and then we'll end with some demos, including a running program in Q#, Microsoft's quantum language.
Okay, that was like 3 new things right there. Did you know there was a quantum computing language?
So my friend another high schooler happens to work with IBM, and he's working on his own computational problems. And I knew that there was like a computational language, but like I couldn't even tell you where to begin with that. Yeah, that's like on a whole other level.
I know C#, I know C++, never even heard of Q#, Microsoft's
Exactly.
quantum language. And also the way he's talking about it is let's see here, Jared called. I missed that joke. But shout out to Shahir. Big shout out Shahir. Okay. Oh. It's from Silicon Valley. And here I'm talking about how I'm such a big fan. No, okay, that is a funny joke. But so he says that we have a running program and we have a computer language. So I guess like this is something that's already being used, like this already exists. Because I remember for years, nerdy me was watching all these different science documentaries about how quantum computers will one day change the world. I was like, oh, that will be cool in like 10 years. I guess 10 years, maybe that was 10 years ago, because I guess we live in the age of quantum computers. So I don't know. Let's see what happens. Let's see what he's got to tell us about it. That's pretty cool, though.
This is the gate quantum computation model. It looks a lot like the classical computation model, where you have like bits and you send them through logic gates and transformations are applied to them.
Okay.
There's another computation model called the quantum annealing model, which is used by D-Wave. If you've heard of that,
D-Wave.
That's something different
from
what we'll be going over.
We're going over it.
They might be equivalent. The jury's still out on that. Anyway, I'm sure you'll have a great time.
I'm sure we will.
So, I'm sure all of you have your reasons for being here, but here are 3 reasons I've come up with if you need some additional convincing why you should learn quantum computing.
Okay.
The first is that quantum supremacy is expected this very year. Quantum supremacy means we have a real problem running on a real quantum computer, which in real time runs faster than the same problem on a classical computer. So Google has announced they think they'll do it this year. If they do, it's a really big thing. So it might be in your future. Who knows? 5, 10 years, we could all be running some really tricky problems on quantum computers.
So this was in 2018, this talk. So Google, do you think they figured it out yet? Have you heard anything about this?
I don't remember the headline specifically, but I did remember Google announcing they had a breakthrough in their quantum computing research. So it could actually be this. But I can't remember the exact details of what was talked about and stuff like that.
Man, Google's
so maybe
so cool. That's crazy. That's crazy. So he's saying in 5 to 10 years we're all 3 to 8 years, I guess, is
But here's the thing, though. There's a theory that every year, like something doubles in the computer components. Like I think it's like the resistors or something like that. Like they increase and get faster and faster every year. So I wouldn't be surprised if Google like nailed this like the following year. Yeah, Moore's law.
Moore's law. That's what it is. Yeah, and then I was reading I was watching another video talking about Moore's law, and that was something that was like kind of new, because you would obviously thinking about that sort of trajectory, it just never seemed like sustainable to me, because like you can only make something so small, and it seems like now the trend has been about, all right, instead of packing more transistors and stuff in there, there's a different principle. I forget what that one's called, but it's the principle that they will only get so small as it is economical to make them that small. And I think IBM has recently shifted from processing power to making new components that don't use as much electricity. So trying to make it as powerful, but like use less electricity. I think that's like what I've read that they're going for right now.
Yeah.
I'm guessing this quantum thing, here's what I'm thinking, like even here's what I'm thinking even going into. I'm laughing at the comments. Is I don't understand if quantum computers just give us double the efficiency, because if something can be, so here's what it is, in case someone is completely not even sure what's going on here. Normal computers, they're using zeros and they're using ones, and that's all they're using, and that's what the computer, if you were to open up your computer and look at all the wires and stuff, there's all these little transistors and all these little circuits and things, and depending on if it's a 0 or if it's a 1, like a gate, like if it's open or if it's closed, or if it's open, this is like a 0, this is a 1, depending on what the 0s and 1s are, it depends what shows up on your screen. And the idea is we can only put so many 0s and 1s in our circuits. If we have a quantum computer and we have this idea of something can be a 0 or a 1, depending on if we observe it that way or not, if we can have a bit which is a 0 or a 1, that's the only thing that means, a bit is a 0, 1. If we can have them be both a 0 and a 1, don't we just double our capabilities like right there? Is that kind of like what you thought about quantum computing coming into this?
Because the way I've worked with hardware and stuff like that, I would assume that that's the technology we already have, where a single transistor could be both. But I thought that was common sense. But now that I see like quantum computers are like so big and things like that, I'm like, okay, we are kind of far away from having a portable quantum computer that can pack all of that. So I think with as we continue to explore the technology and things like that, obviously there'll be advances. But me personally, I just assumed that computers could have that capability of it being both, but I guess not.
I don't know. That's what I thought. I don't know. Maybe, let's watch some more. Maybe we'll get a little bit farther into this.
So we have lots of large companies: Microsoft, Google, Intel, IBM. They're all
They forgot about McDonald's, the quantum supreme.
Billions of dollars in quantum computer development. There are lots of really exciting applications. This is the one that everyone's heard about: Shor's algorithm.
Yes.
When this paper came out, it lit the world on fire. People were like, wow, quantum computers could actually have real economic impact.
I remember that.
We could factor RSA and undermine our global financial system, which is pretty cool.
Pretty cool.
Here's one that programmers will, I think, appreciate, which is we can search an unordered list in square root n time. So you think for an unordered list, you have to check every element.
Yeah.
That's on. You can just get a nice speed up, just square root n queries on a quantum computer, which is pretty nifty, generally useful. And here's the one which I think.
What do you think about that, Elias?
That makes process. Wow, that's actually interesting because now you could speed up virtually everything.
Yeah.
That's pretty cool.
I'm now just getting into the part where I'm like messing with these sorts of algorithms, and that. What if I did that? What if I walked into a coding interview and dropped some like, yeah, this is O of n, but honestly, if you did this in Q sharp, like you can do it. It doesn't even, it doesn't even. This is O of n squared normally, but on quantum, I've coded something up in Q sharp. You know about Q sharp. Shor's algorithm. Shor's algorithm. It lit the world on fire.
Literally.
So you use that and it takes 2 seconds. Yeah. But that's kind of crazy. All right, let's see.
Yeah.
It's probably is the best probability of changing the world. Sorry, programmers, square root n search probably won't change the world too much. Which is we might be able to have an exponential speed up in simulating quantum mechanical systems. So things like drug design, if you simulate like biological molecules interacting, things like that,
cool.
it could like massively speed up a lot of our biological research. And everyone talks about like nitrogen fixation for this. That's like part of the main Microsoft sales pitch. But
nitrogen fixation.
This is the one that actually motivated me, the bottom one, which I think from talking to a couple of you before the presentation began also motivates you. It's intellectually interesting. And it's interesting because it's just kind of outside my intuition. Like I think all of us at this point in our careers can basically look at any digital or mechanical system and have like a ballpark idea of how it works, right?
Yeah.
But if you look at a quantum computer, like how can a quantum computer outperform classical computation? It doesn't make any sense.
It doesn't.
Like there's no way I could even like start to guess.
There's no way. Yeah, I agree.
And so I really wanted to learn it. And I think there's a reason for this, and this is kind of getting a bit philosophical. But our language, our informal language that we use, developed in a very classical world. It is simply not equipped to deal with the quantum world. And this is why any pop science article you've read on quantum phenomena, it doesn't really ring true. All the metaphors, they don't really make sense.
That's right, they don't.
Because we're trying to express it in this language which developed in a classical world. We need to learn a new language, which is the language of mathematics. And that is the only thing which will actually let us understand quantum mechanics, is to learn it mathematically. All metaphors and analogies will lead you astray. There's a famous quote here by a physicist named David Mermin, which is, "Shut up and calculate," with regard to quantum mechanics. So some grad students, maybe they lean back in their chair and they're like, oh, what does this all mean? Shut up and calculate. Just trust the math. The math is the only thing which will not lead you astray.
Okay. Sounds good.
Here's how this presentation will break down. First, we're going to learn how to represent computation using super basic linear algebra, matrices, vectors, matrix multiplication.
I can do that.
Then we will generalize that to learn about qubits, superposition, and quantum logic gates. And finally, we will use all of.
I like the word qubits, though.
It's a fancy word.
Yeah, qubits. I like that. I like that.
I'll add that to my
developed
vocabulary.
to go over the simplest problem where a quantum computer outperforms a classical computer. This is called the Deutsch Oracle problem.
Deutsch.
I mean, there are a bunch of problems, but
I
this is the
said
simplest.
Dutch. My bad.
And finally, it'd be almost negligent to let you get out of here without learning about quantum entanglement and teleportation, just because with the tools we'll develop, they're like so easy to understand.
I'm
So
going
we'll
to
have
skip to
bonus
that
topics,
part.
and then we'll
We're
have
not
some
getting
demo.
out of here
Oh, yeah,
without learning about
100%.
All right,
teleportation.
let's get to it. You'll become very, very familiar with these two vectors. This is how we represent a 0 and a 1.
Real quick.
Okay.
The two values of one bit.
For those that don't understand vectors and matrices, you think you could do a quick little, just a basic
Yeah.
understanding of what a vector is?
Yeah. Oh man, if I had a whiteboard, I gotta write that down. I should have it for next time. So, matrices and vectors. This is from someone that's only experience in linear algebra is having another student at Make School very slowly explain everything to me, and and then I did some Khan Academy. And so I've done matrix multiplication. I've messed with vectors before. Essentially, how can I do this? So you have let's say you have like a number line. So you have a line and then you put a 0 in the middle, and you do 1, 2, 3, 4. And then you go the other way, -1, -2, -3. And then you have another line going up and down. And it's the same thing, like a graph, like graph paper. So you have your graph, and then 1, 0 is like your location on the graph. Go over x1, 0, y. So I'm on this point. And so that matrix, that 1, 0 could represent that dot on that graph.
Okay.
And now in computer science terms, we look at this 1, 0, and we kind of start thinking like, oh, that kind of looks a lot like an array. Like when I go to a linear algebra matrix, and I start looking at this crazy stuff, like this thing all the way on the left, it looks like just a big old array, just like a 2D array. And that's kind of what it is. And then you can multiply this 2D array by this other array, and then you can get another position, and you can do transformation. So like, how do I take something in like 3D space and then transform it into like a 4-dimensional space? And that's what linear algebra lets you do. Linear algebra lets you take a graph and then apply math to it. That's what linear algebra does, doing math on graphs and stuff. And then calculus, of course, is more like acceleration and force and all of that sort of stuff. Linear algebra is more about like, I guess, like absolute space and the geometric connections between two objects on a space. And it's really useful for like computer science because of reasons. But that's I think the best I can explain it. So when we're looking at this, a 0 and a 1, I guess in this, let's see here, representing classical bits as a vector. These classical bits, of course, are the 0s and 1s in the computer, making the computer work. And now we're just taking those 1 and that 0, and we're going to represent it as a vector. And let's see what happens with that.
These two vectors. This is how we represent a 0 and a 1. The two values of one bit in classical terms.
Okay.
So the top one is just 1 over 0, and the bottom one is just 0 over 1. You can also write them in that weird like angle bracket thing. That's called Dirac vector notation. So you have a 0 in there. That means this is the value of that vector. If you have trouble remembering this, just think of it like an array indexed from 0. And so
that makes sense.
There's a 1 in the 0th index. That means it's a 0. There's a 1 in the first index. That means it's a 1.
Okay.
Okay. Everyone.
Are you fine with this?
Yeah, I'm good.
That makes sense, right? The array. Yeah. Okay. Yeah. He did it better than me. I think that makes sense. Okay, cool. Let's keep going.
Fine with this? You'll be very familiar with this by the end of the presentation.
I bet.
We're going to go over matrix multiplication really quickly.
Yeah, this is what matrix multiplication looks like.
Yeah, we're going to see that. OK. The way to think about matrix multiplication, just to review it for you, most of you will have gone over this in your linear algebra courses, like the first or second day.
So
if you have a matrix multiplied by a vector, you kind of like take this horizontal row and then flip it and multiply it pointwise with these vector values. So a times x, b times y. And that's how you get the top one. Then you do the same thing with the bottom row. C times x, d times y.
You got that, right?
Mm-hmm.
That's what with a, and then you do the x, and you got to go for the b. Yeah, it's not that hard. It sounds really hard, but it's not
Yeah.
Oh, just take the A and do the X and the B and then do the Y and then do the same thing in the bottom, C and the X and the D and the Y. And then there you go. You multiplied the matrix.
The 2 vector. The same thing happens with 3 by 3 matrix, A times X, B times Y, C times Z. And you get this
Z,
matrix.
huh?
You can also this vector, you can also multiply matrices together. We won't really be doing much of that.
No.
And there's a very special matrix called the identity matrix, which has zeros everywhere except for ones along the main diagonal. And anything multiplied by the identity matrix is itself. It's just like multiplying by 1. In fact, usually you refer to the identity matrix by the symbol 1. Now, thankfully, for simplicity, a lot of the matrices we'll be using look a lot like this. They're mostly zeros with just some ones. And you can notice, is a nice rule of thumb, that relative to the identity matrix, this matrix has the middle 2 rows flipped. Okay?
I did notice that.
And that's actually the action it has on anything it multiplies. So it flips the middle 2 rows. It's a nice sort of rule of thumb to remember how matrix multiplication works. Does anyone have any trouble with this? Because you really need to know this in order to go ahead.
Okay. He feels pretty strongly about that. So how do you feel about that?
I'm good. I understand.
I feel pretty good.
Yeah, I'm good. I'm sure.
Twitch chat, how do you feel about that? Are you following along with this? I think let me see if I can scroll back and not, what am I, 729? Yeah, right here. No, I feel 720. Yeah. All that's different in these two is that these middle values are flipped. This is 1 and 0. Over here, it's a 0 and a 1.
Yep. Yeah. Basically.
Yeah. This is what gets me suspicious, though, is because I understand this, and I feel like he's about to drop something on me, and I'm not going to be ready for it. But
oh yeah,
I feel
that's exactly
right now
what
I'm
it sounds
fine.
like.
To remember how matrix multiplication works. Does anyone have any trouble with this? Because you really need to know this in order to go ahead. You got to know it. Okay, great. Operations. Actually, I'd like to make this a quiz. Can anyone tell me what are the 4 operations on 1 bit? There's 4 of them.
Add, subtract, multiply, divide. I don't know.
1 bit.
And or exclusive.
Those are on 2 bits.
Oh.
Oh, not identity.
Identity, not.
Set to 0, set to 1.
Set to 0, set to 1. There we go. Good. Yes.
That was
we have
close.
identity. Just f of x equals x. Negation, fx equals not x. Constant 0, it's always set to 0. Constant 1, it's always set to 1. You can see with the diagram how it kind of looks. Okay?
Okay. Now that I see the graph, I'm good. Identity. So the only thing we can do on 1 classical bit is identity. We can negate it. Always make it 0. Always make it 1. Interesting.
That makes sense. Yeah. So far, so good.
Okay. Not drowning yet.
And we can write these as matrices. So the identity is just the identity matrix. This, remember, is our symbol for 0.
Of course.
Identity multiplied by 0 is 0. Identity multiplied by 1 is 1. Here's negation. You flip it from 0 to 1 and 1 to 0. Same thing for constant 0, constant 1. So I hope I've convinced you we can represent very simple functions, at least, with matrices multiplied by our 0 and 1 vectors. Okay.
Okay. What's he drinking? Diet Coke?
And remember these 4 functions, because I will quiz you later on them.
This guy drinking Diet Coke talking about,
Oh, no.
Back up. So let's talk about reversible computing.
Okay.
Oh, God.
Reversible computing is a neat sort of buzzword. If you ever read the popular sci-fi book Accelerando, it talks about reversible computing. And basically it means...
You ever read Accelerando?
No, have you?
Of course. Who hasn't read Accelerando? I don't know what that is.
If I tell you the operation I did and the output of that operation, you can always tell the input of that operation if the operation is reversible. So intuitively, operations that just shuffle bits around, like permute them, they are reversible. But operations that like erase bits and then overwrite them are not reversible.
Okay.
And in our previous slide, identity and negation are both reversible. Because if I say the output is 1, and I put it through the negation gate, that means the input was 0. You can always tell that. But if I say the output was 1, and I put it through the constant 1 operation, you can't tell what the input was. It's not reversible. It erases information.
Right.
And the nice thing about quantum computing, which you can remember, is that quantum computers only use reversible operations. Those are the only ones we care about. So the only operation we actually care about on the slide is really negation. Like also identity, but it's the same as doing nothing. A further fun fact about quantum computers.
Is there a philosophical statement there? There's also identity, but that's the same as doing nothing. Huh. By doing nothing, we are expressing our identities. Interesting. At least in computers. So reversible, I'm pretty good there. Okay. So those, okay. I feel pretty good. We want to, I don't know why we want to know why we want reversible computing. I don't know. I'm thinking we might get to there soon.
You know what this reminds me of? I don't know if people have seen the movie Tenet, but this reminds me heavily of that, where they go, basically, they're going back in time, but time still moves forward. It is the most like mind warping movie you could ever watch.
That
But,
is
yeah.
trippy.
Yeah, it's weird.
That is weird. Okay, let's see.
Is they actually only
What was
use.
that movie called?
It's called Tenet. Tenet.
Oh, is it on Netflix?
No,
Oh,
sadly. Yeah.
I guess I'll download it illegally.
Operations which are their own.
Or Amazon.
inputs.
They probably have it.
Not only are they reversible, but if you apply them twice, you'll just get back the same input value. And we're going to go in a little, this is kind of like getting into pop science, but whatever. There's something called the von Neumann-Landauer limit, which is the smallest amount of energy.
Okay, the subtitles were way off there. It was, okay, or maybe it was on.
saw
I
a-
don't really know.
Yeah, I saw a V and I'm like, wait a minute, that is not the
Launder.
same.
Hold on.
That is
See
not
that
the
again.
same.
All right. The von, I would say von Neumann van der limit. And I thought that was a sick name, and I couldn't wait to hear him say it. And then he says,
Von Neumann-Landauer limit, which is the smallest
I don't
amount
know. No clue.
of energy physicists have calculated is necessary for the simplest possible calculation, which is non-reversible. And reversible computing might eventually let us go beyond that limit, more efficient than that theoretical limit. Now, currently, processors are use millions of times more energy than the von Neumann-Landauer limit. But 50, 100 years from now, who knows? Pretty nifty.
50. I think the computer knows better than we do, because he said 50, 100, and then the subtitle said 5,000 years from now. So.
Yeah. Subtitles
Maybe.
on point.
The computer.
Oh.
Hello, Reshirk 203. You came just in
What's
time.
up?
We're doing the review tensor product of vectors. Let's see what he's talking about.
All right. This is something you probably did not go over in linear algebra, but don't worry. It's still pretty simple.
Good.
It's called the tensor product. So if you have the tensor product of two vectors, it's kind of like you take the second vector and you tile it for each element in the first vector. So x0 gets its own copy and x1 gets its own copy.
Okay,
And
that's
then
not
you
that
multiply it out, so you get eventually x0, y0, x0, y1, etc. It might be easier to look at this with real numbers. Here we have 1 times 3, 1 times 4, 2 times 3, and 2 times 4 to get this.
Okay.
Oh, okay, I got that.
Here's how it looks like with 3 vectors. You get this like giant array. Don't worry about it too much. And
I wasn't
I'd like
going
to point
to.
out that
Yeah, I wasn't planning on
if we
doing
use
so.
our 0 and 1 values, you end up with a vector which has a 1 in only a single position. Okay. Does anyone have any real trouble with this concept? If I gave you 2 vectors, you could probably calculate the tensor product.
Easy.
It's not entirely difficult. All right, but the final point I made leads into how do we represent multiple classical bits?
The PTSD from machine learning. No, this is good. This will not give you PTSD. This is good. We know what's going on here. Sort of, I guess.
Oh man.
All right, now we're representing multiple cbits. This is all very interesting. I'm really curious where he's going with all this, though, because I don't know.
Same.
I
And
couldn't
we
tell
represent
you,
them by their tensor product.
but I bet you will know.
So 0, 0, remember we tensor, this is our 0 symbol.
Okay.
0 tensored with 0 is this product state, we call it.
Product state.
0, 1 is this product state.
Okay.
1, 0 is this product state, like 0 times 1, 0, 0 times 0, 0, 1 times 1, 1,
Hey.
1 times 0, 0.
Oh,
Okay, and 1, 1 is this product state. And similar to just the single bit, you can think of this as an index in this vector array. So this is 0. There's a 1 at the 0th position. This is 1. There's a value at the first position. counting from 0. And this is 2, value at the second position, 3, value at the third position. Okay? This is the only time I will tensor 3 bits together, thankfully, because as you notice, they grow exponentially in size. But it works for this. So 4 is 1, 0, 0. You have 0, 1, 2, 3, 4 is where the 1 bit is.
Right.
Okay. Yeah, so we call this the product state. We can always factor it out into its individual states. And the product state of n bits is a vector of size 2 to the n. Here we see a sort of whisper of the power of quantum computing, this exponential term. But hold that thought. We'll get back to it.
Okay, holding it.
So we're going to learn a very important operation, very fundamental to reversible computing and quantum computing. It's called CNOT, or conditional not.
Kind of want to
It
skip
operates
this part.
on a pair of bits. You designate one bit the control bit.
I want to
and
see
we're
where he's
applying it to our
going with all
product
this.
state.
All right, C
We're
naught.
just going to flip the bottom 2 rows.
Flip the bottom 2 rows.
So we get to this product state, which when we
Okay,
factor
what else do we got?
0 then, or sorry, 0, 0, 0. So the control bit's 0. That means we're going to leave the other bit alone, right? And we see that indeed this is what we do, and same with for 0,
I'll
1.
leave the computer to
Okay, so
to handle this math for me.
everyone, well,
Yeah.
maybe you're familiar with
Yeah,
how
exactly.
classical computers or like real CPUs, they're all built on the sort of NAND gate. Like everything is fundamentally built on NAND.
And.
And the CNOT is kind of the analogous NAND for reversible computing. It's like a really basic thing that is used to build up larger, more complicated logical statements. Like, so I'm sure if I gave you a task, like build some more complicated logical formula with CNOT, you'd probably be able to do it at this point. You just like stick them all
No, I
together.
wouldn't.
Eventually it comes out.
Easy. Yeah, no, I could do that.
I will note that it's not actually universal. You
shouldn't
can't
skip
make
something.
every logical function with a CNOT gate. You need something called a Toffoli gate. But
too
we
many
won't
gates.
see that.
Toffoli
in this
gate.
presentation.
Crazy.
And we've learned everything we need to
think it's in
know
Italy?
about how to use linear algebra, to represent classical computation. And we can now go on to quantum computing.
Okay,
So to
let's do
recap,
quantum computing now.
we
Let's
learned that we
go
can
on to it.
represent classical bits in vector form is 1, 0 for 0 and 0, 1 for 1.
Okay.
We can represent operations on bits by multiplications on their bit vectors. We learned that quantum computers only use reversible operations. And in fact, the operations are their own inverses. And multi-bit states, we write, is the tensor product of our single-bit states. Finally, we learned about CNOT, which is a very fundamental gate in reversible computing and quantum computing. So this is everyone's following along so far? This is pretty
100%.
simple, right? It's not that bad.
Not that bad. Let's have some
Exactly. A 2-year-old
Diet Coke
Okay,
to enjoy.
let's make the jump. Qbits. And I will surprise you, we have been using qubits all along, actually.
Oh, this is where the square root comes
cbits
into play.
are just special cases of qubits. And we represent a qubit in general by a vector of 2 elements, A, B, where A and B are complex numbers. Don't worry, we'll only use real numbers for this presentation. We're keeping it simple, only using real numbers. And we have the constraint that A squared plus B squared is 1. So 1, 0, and 0, 1 fit this definition, because 1 squared plus 0 squared is 1, and 0 squared plus 1 squared is 1, right?
Okay.
Basically,
Now, here
yeah.
are some example qubit values. This is one with which you'll become very familiar. It is 1 over root 2, 1 over root 2. Can anyone tell me what 1 over root 2 squared is?
Can you tell me?
Nope.
I can tell you it's 1/2.
Oh yeah.
1/2, exactly.
Yay!
1/2 plus 1/2 is 1. So
Hooray
this
for
is a
subtitles.
qubit. What about
Oh
1/2
God, I didn't even check
and
that.
root 2 over 2? What's 1/2 squared? 1/4. So 1/4 plus
What's up,
3/4
Ian?
is 1.
Source code's in the
Here's
building.
an interesting
My
thing. We
dogs.
can actually use negative numbers now.
Oh, everyone's wishing me
Because a
happy
negative number
birthday.
squared is a positive
Yay,
number.
happy
So
birthday,
negative 1
me.
squared is 1. 1 plus 0 is 1. And
Appreciate
same
you.
thing here. It's just the same as this first matrix. but
This
one
is what I
about-
want to do on my birthday. I want to hang out with all of you and learn about these qubits. What more could you want?
That's a weird way to spend it, but hey, gotta do what you gotta do.
You gotta do what you gotta do. My goal is to one day be able to afford a shirt like this guy's got on it. That's one of those shirts that, like, you know, it looks like you could get on sale at Macy's, but I bet you it's like $120. Good for him.
Yeah. He works on
You
Microsoft,
deserve it.
so-
You deserve it if you're doing this sort of linear algebra craziness. Very special qubit birthday. Brian is the cool guy. Galactic Bacon, my dog. Best type of bacon.
Galactical.
Pretty neat. Not bad so far, right? Okay, but you might.
Oh, someone just asked, what is a qubit? All right. We just watched this video, Elias. What would you say a qubit is?
It's the type of bit that's inside of a quantum computer.
Yeah.
And the And the only type of operations it accepts is reversible. What is it? Reversible what?
Yeah, reversible operations. I think it was
Yeah.
reversible states.
Yeah.
Yeah. That's what
that's
what
that's
a
as much
qubit
as I
is.
can tell you.
If you want to know more about qubits, I guess you can watch the replay of this episode and start from the beginning. But yeah, it's something that's used in quantum computers, basically. It's a bit for a
Exactly,
quantum
yeah.
computer. That's I think the highest level we can talk about it. Yeah, you don't know anything about quantum computing? Me neither. That's why we're watching
None
this.
of us do.
Yeah, quantum bit. That makes sense. Yeah. Okay, here we go. So how can a qubit have a value which is not 0 or 1?
This is kind of like saying that a qubit has a value which is not 0 or 1, but actually both 0 and 1 at the same time. This is called superposition. Everyone's probably heard of the Schrodinger's cat being both alive and dead. That's just like a pop science-y way of articulating this concept, sort of. And the interesting thing about a qubit being in superposition, it means we can kind of, I want to really qualify this, kind of compute with the values of both 0 and 1 at the same time, which again is the sort of whisper of some quantum speed-up power.
Yeah.
Okay. Now, how this works is when we measure this qubit, it collapses to our familiar values of 0 and 1 with some probability. And this is what we usually do at the end of a quantum computation to get the final result. We send it through the measurement gate. We see what the result is.
Dude, that's crazy. I called it. Yeah, that's exactly what has to happen. Okay. So in a classical computer, we have zeros and we have ones, and that's binary. And we all know about zeros and ones because, that's how you make fun of nerds. You go up to the nerds and you go, hey, 0, 1, 0, 0, 1, 1. What did I just say? And so that's classical computers. But with quantum computers, now we can make fun of nerds in a whole new way because we can say 0, 1, 1, 0, 1, 0, 0 and also mean the exact opposite of that because of superposition. And the only way we know what those zeros and ones are representing is if we measure them, because that's what's going to give us, it's going to collapse it into, it actually has to be a 0 or a 1. It can't be both. But we can perform calculations, he says, sorta, as if they are both a 0 and a 1. And it's only going to matter, it's not going to matter until we measure what's going on. So it goes through a measurement gate, whatever that is. I don't know how you would make such a thing, but that's what's going on here. You can perform all the calculations and then get your end result past the measurement gate. Okay, cool. See here, same hashtag Silicon Valley qubits like Schrodinger's bit. Yeah, exactly. Yeah, okay, so Schrodinger's cat, so you know what's going on here. That's all that's going on is this is Schrodinger's, such a hard word to say, Schrodinger's cat in zeros and ones, and Schrodinger's cat for computers, basically. Yeah, and that means you do speak a little bit of nerd galactic bacon. Welcome to the club. Here we go.
So how the probability works is if you have a value AB, it collapses to 0 with probability A squared and 1 with probability B squared. So if we look at our familiar qubit from the previous slide, 1 over root 2, 1 over root 2, it has a 1/2 chance of collapsing to 0 and a 1/2 chance of collapsing to 1. It's like a coin flip. Now, if we just measure our classical qubit, or classical cbits, the 1, 0 has a 100% chance of collapsing to 0, and 0, 1 has a 100% chance of collapsing to 1. So it's sort of idempotent in that way. And I found it useful here to give people a sort of physical intuition about what we're doing, what a cbit is, or a qubit is. If you've heard of polarization, you've probably bought like fancy sunglasses. It says that they're polarized.
Yeah, I know. Yeah.
So polarization is actually a sort of quantum phenomenon. You can be polarized like this way or this way, and your glasses will only be polarized a certain way, so they'll only let light polarized in this way through, basically. It turns out that qubits, you can think of like this, a photon being polarized this way is a 0, and a photon being polarized this way is a 1. Superposition means it's actually like both, right? So it could actually go through both gratings. And then if you measure it, and a way to measure it is just to like fire it through a grating and like see whether it goes through, then you can collapse it to 0 or 1. So that's our sort of intuition, pinning this to a physical concept. Of course, we found that photons actually make very poor qubits. They tend to collapse too easily, so we don't use.
What was that?
I thought we said no physics.
Yeah, right?
But that's an interesting concept.
That
That's
is an interesting concept.
Okay.
Oh, man. All right, that's all right. I'm good.
Those, but you can
Yeah.
maybe think of that.
Have some Diet
Does anyone
Coke.
have any confusion here, really, about how this measurement process, collapse probability works? Okay, great.
Do you think when you're watching, like if you're in the room with this guy and he's given this talk and you're with a whole bunch of other people who like are here for this talk, do you think anyone's asking questions?
No, and I think I
Yeah.
personally wouldn't ask questions because I wouldn't want to feel like the one
Right.
person who does.
I guarantee you the whole room is just sitting around and they're just like, yeah, and no one knows what's going on. I would ask questions. I'd be there in the back, my hand raised. What are you talking about? And go through the glasses both ways. What do you I don't know.
What do you mean by that exactly? Yeah.
Yeah, can you start from the very beginning again? I kind of missed all of that.
Oh man, that'd
We
be
will learn
funny.
about multiple qubits. The same is multiple cbits.
I want
We
to know
represent
where
them
this
by
is
the
going
tensor
because we
product.
only have 10 minutes left and I want to learn about teleportation. Where do you think he talks about teleportation?
It'll probably
Teleportation.
be the
Oh, right here.
bonus. Oh, there we go.
112. All right, let's jump ahead to teleportation. I will
Is
leave it to
feet.
you, dear viewer, to watch the rest of this video. I don't want to spoil the whole video for you. I know you want to watch this all night, take notes. So let's go to teleportation here. This slide says teleportation. Is there another slide that says it?
There is.
Okay, there's another slide. I want to get to the very beginning of it. Oh, here's a dude asking a question. Risky business. Here's another dude asking a question. Okay.
Oh.
Yeah, that was the bonus question. That's probably bonus.
Entanglement.
Okay.
So I'm guessing that's the first slide then. Should be after that guy
Okay. Bang.
right there.
Teleportation.
That we do that. Okay. All right, let's move on. Teleportation.
Yeah.
This is the actual use which you asked about. And you've probably read about quantum teleportation again in pop science articles. Needless to say, their explanation was complete trash. Made no sense at all. But now it will make sense to you. Okay? It's the process by which we take an arbitrary qubit state
Chat's cracking me up.
and transfer it across space and time somewhere else. So you use entangled qubits as a sort of bridge to send a qubit from one place to another. And here's a very important thing. It's called the no cloning theorem.
No
You can
cloning
transfer
theorem,
qubit
okay.
states, so you can cut and paste them, but you cannot copy them. You cannot copy and paste a qubit state. You cannot clone it. This is called the no cloning theorem.
Oh, makes sense.
It's actually pretty simple to
Why?
prove. You just show that
That
any
makes sense because if I was able to clone it and copy and paste, if I was able to copy a bit from here and then paste it over there, then that would be like violating the speed of light. That would be like violating physics because I'm taking a physical thing and then moving it over there. But if no, because he said the opposite. He said you can cut and paste. So he's saying with quantum entanglement, if I can take one thing, I can cut that. So I have to move it. Yeah, I have to move it from here.
Oh,
Okay.
okay. I think I get it. So basically, you can move it through time, but you can't leave the current one, copy it, and paste it somewhere else.
Yeah.
Like they can't. I'm guessing they can't exist at the same time.
Yeah. That's
Something like
good.
that, maybe.
That's
Something
good.
like that.
I think we cracked the code on that one. Yeah. We can. Yeah. I think you said it perfectly. I'm not even going to try and improve it.
Oh.
That's good. Okay. So let's see.
Okay.
That's cool.
such operation would not be reversible or its own inverse. But we're not going to go do that. And here's an important thing. The teleportation, despite using a faster than light phenomenon of entanglement, is not itself, the whole protocol is not itself faster than light for communication, because you actually must exchange two classical bits. So if I'm teleporting my qubit to you, in addition to us having an entangled qubit pair, I also have to send you 2 bits of information. And we'll show why that is in the next slide.
Not
Does everyone
sure
kind of
what that
conceptually
means,
grasp the, I guess, the purpose of quantum teleportation?
but I want to see it.
Okay. So here's what the circuit looks like. We're not going to go over the math. There are appendices to this slide deck, which you can see after the class to go over the math, but it gets a bit complicated, so we're not going to do it.
Okay.
So we have
me.
the qubit that we want to teleport here. We call it T, and its value is phi. It's just this generic qubit value. It can be any value. And then we have these 2 qubits, A and B, which are both initialized to 0.
Okay.
Now you'll recall this is the entanglement circuit. So these
So
two
it's like a
qubits are
bridge.
entangled. All right.
Yeah.
Okay.
Now, after they're entangled, we'll say we have Alice and Bob.
Alice and Bob.
Alice wants to send her entangled qubit to Bob. So Alice has these two qubits. Bob has this qubit.
B for Bob.
And these two qubits are entangled.
B for Brian.
So the qubits are like, these two qubits are separated right after being entangled, basically. Now Alice then entangles her qubit she wants to teleport with the other two qubits. So it's a 3-qubit entangled system. If you were to write out the product state, you wouldn't be able to factor it into 3 qubits. Then she puts this qubit through the Hadamard gate. Finally, Alice measures both qubits in her possession, and those are the two, and this results in 2 classical bits. These are the 2 bits that Alice has to send to Bob.
Okay.
And the measurement result of this bit determines whether Bob has to put an run his qubit through an a bit flip gate, and the measurement result of this qubit controls whether Bob has to run his qubit through a new type of gate, which we haven't seen before. It's called the phase flip.
Oh, that's crazy.
Gate, or Z, and this is what the matrix looks like. That's
really
basically,
crazy.
once Bob has applied those 2 gates, or neither gate, if both of these end up being 0, Bob doesn't have to apply anything. He'll end up somewhat magically with Alice's qubit value she wants to teleport. Pretty nifty, huh?
Somewhat magically, he says. How does that value get over there? I get what's... All right, here's where I'm at, Elias. I get the idea of we're going to have that T and the A. These are going to be 2 quantum bits. And so the A, quantum bit A, I entangle with B. Quantum bit T, I entangle with A. And then when I go, once they're entangled, and then I go and I measure those 2 bits because of quantum mechanics and entanglement theory, I hope chat has like a little bit of background with quantum entanglement. Like the thing is the same here as is the same over there. Like they're intertwined and they relate regardless of time and space. Like they're these 2 linked things. Quantum entanglement. So when I measure my thing over here, that is affecting, or it's determining its state all the way over there with Bob.
Yeah.
So that's a way that I can transfer that data, not faster than light, but I can transfer that data, and probably much quicker, because whatever I observe, it immediately becomes for you. And I guess in some sense it always was that. Now, what I don't understand is how the value of tau gets all the way down there. What was
because of the entanglement. So you see the bridge between T and A?
Yes.
That's the physical entanglement between those 2 values. So it's being passed down, and because A is entangled with B, the T gets transferred all the way down.
Oh.
You get it? So if that bridge wasn't there between A and B, T would stop at A. You get it?
Yeah. That's crazy, because we've already entangled A and B.
Exactly.
Oh, bro, that's crazy.
Yep. It's at first it's a bit weird, but when you try to like compare it to like when you try to understand it using non-mathematical terms, it's a bit easier. So like, when he said that this entanglement is like a bridge between these 2 bits, I was like, okay, so they're connecting each other and they're relational. So that's how I was able to get it.
That's what throws me off, is the math people start throwing in these terms at me, and I'm
exactly.
I don't know, but okay, when I hear you say that and I don't use any math terms at all, conceptually I'm good. And that is, let's keep going.
Pretty nifty. And you might be like, well, we're already exchanging a qubit here. Why do we even care? Like, we're obviously just giving a qubit to Bob. Like, couldn't we just, Alice just give her a qubit, like, right there? So what you can do is you can pre-entangle, like, a whole bunch of qubits, like a few billion qubits or something. And then you ship them by mail. They're called EPR halves. You, like, ship them by mail or something. So Alice and Bob have, like, a big repository of these entangled qubits.
Like email or physical? Is it physical? Do you have to actually?
I think they meant through like electricity or something, but I'm not too entirely sure.
just the idea of like we have to use this quantum entanglement, but in order for it to work, we need FedEx to get involved. It's just a weird concept to me. Okay.
Let's call Amazon real quick. Overnight shipping.
But the idea of having like
Mhm.
pre-arranged entangled bits, that makes sense to me.
Mhm.
Wants to send a qubit to Bob, she can just use up one of the EPR pairs, EPR halves. EPR pairs. And at that point, that EPR pair has been collapsed, can no longer be used. So it's a non-renewable resource. But Alice can just send as many qubits as she wants over to Bob. Okay. Now you might be saying, well, I don't really get this. The math is in the appendix. If you really want to go,
God.
It gets pretty
appendix,
complicated.
you say.
Okay. But I think I did an okay job of explaining it. So. Okay. You might be like,
good.
okay. Oh, by the way, I forgot to say.
I was about to end the
Really
video.
cute,
Okay, good. Really important thing.
You may have heard that we can simulate quantum computers on a classical computer, but it takes exponential slowdown or exponential memory. This is the reason. If two qubits become entangled, you have to keep their full product state around. So if like n qubits become entangled, you have a vector of size 2 to the n you have to keep in memory. And that is why it takes exponential memory
because we have to
simulate a quantum computer.
We have to save
on a classical
both
computer.
0 and 1 states.
Pretty nifty. Okay. So you may be like, okay, this is all pretty interesting. Further learning goals. You can learn the Deutsch-Jozsa algorithm. That's the one with n bits that I talked about. And also Simon's periodicity problem, which is another figure out some property about this function. I'm not going to talk about the complexity stuff. But anyway, you can also learn Shor's algorithm, Grover's algorithm, quantum cryptographic key exchange. That one's actually pretty simple. I recommend looking at that. You can learn how they're actually implemented in physical terms if you care about that. An important thing, quantum error correction. Since these systems are so small, like a spare cosmic ray can just come out of nowhere and just wreck your entire computation, you need very, very stringent error correction schemes. So I think theoretically, it takes 5 physical qubits for a single logical qubit like we've been operating at. In practice, it's looking more like we'll need 100 or 200 to get like a qubit of like 100%
So we have some backups in case something goes wrong.
Exactly.
So that's something to keep in mind. Like when we see like Google's coming out with a 30 qubit computer, it maybe doesn't mean as much as we'd hope. It may only get us like 2 or 3 really high quality qubits. And also quantum programming language design, which I will go over because I'll show you a
I want to see the Q sharp. I was about to Google it. I want to see the Q sharp.
Example. But anyway, recommended textbooks. This one is my absolute favorite, has the same title as the name of the talk, Quantum Computing for Computer Scientists. This algorithm is by our friend David Merman, the Shut Up and Calculate guy. He holds up the textbook and like,
this algorithm was made by this guy. like the whole book is just, this is the algorithm. 500 pages of algorithm.
Oh, man. Also,
I started out with this one. It was horrifying. It was just like, but it skips.
Oh no, I just wanted to respond to Galactic Bacon. He said that we need to ship it by mail so that someone can give their appendix, and that's actually how it works. That's actually how it works.
Yeah, no, that makes sense. Okay.
Yeah.
That's why people said in the past, like, you don't need your appendix, is because we didn't figure out quantum computers yet.
Exactly. Now we understand why.
Now all those people got rid of their appendix. Good luck getting a job at Microsoft. Okay. And Reshirk thinks of episodes poggers. I agree. I totally agree with that one. Okay.
Oh yeah, 100%.
Oh, no, I didn't see the note. I can't see chat. Okay. Channel to rate whenever ready. All right. Let's wrap this up and then we're going to rate a channel. It's going to be a good time.
Sweet.
A lot of steps, basically. It's more symbolic manipulation. You won't see as many vectors and matrices. I like to write out the vectors and matrices to see what's going on, which gets really unwieldy when you're writing out like a 64 by 64 vector or matrix. But I like to have both of these, you know? So I'll use this to fill in the gaps with this. This has more interesting asides, stuff like that.
Show me the Q
sharp. MS library. There's another one called Quantum Computing. Okay, the first demo.
And then I'm done. I just want to see the Q sharp.
Just the Deutsch Oracle problem in Q sharp.
Based on F sharp.
So
okay,
Q sharp
now you're just making things up.
And
well, F sharp is a language.
We have this function I've written is black box constant. You take in a black box and I tell you whether it's constant. Oh gosh, sorry. Here, of course.
Let me make this bad boy bigger.
We have our function is black.
Okay. I just want to
They're
look
doing
at
it
it.
in VS Code. That's pretty cool.
Yeah. Okay, so I can do this then.
All
Box
right.
constant, where it takes in a black box and it just returns a bool. Is it constant or not? And it just uses the same protocol we went over. It allocates two
.qs
qubits,
file.
calls one input, one output, clears them, sets them both to 0, does the pre-processing, flips them, puts them through the Hadamard gate. Then it sends them into the black box. Afterward, it again puts them through the Hadamard gate, and then it measures both of them. And again, if the input result is 1, then it's constant, otherwise it's variable. Okay? We have our black boxes defined here. So constant 0, again, remember it's nothing. For constant
This
1,
is sick.
we
And also the
flip
language
output.
doesn't even look that crazy.
Right.
Like I really like
this.
the way
I
this is written.
understand.
Yeah.
Like this I understand. It's not too bad.
You know, the talk for computer scientists, maybe we should have started this. Yeah, I don't know. I don't know. The voice in my head told me that I can't see a definition for X or any of that stuff, and I agree. But that's the thing with new languages. I never know what's baked into the cake and what's magic and like what's built in or not. So maybe that's a built-in thing, or maybe we define somewhere X somewhere else. I don't know. Because the X is blue, so it makes me think that like
For
the linter at least recognizes it, just like it would recognize CNOT. I wish I knew what it was.
We
though.
run a CNOT gate with input as control, output as target, and negation we use CNOT and X. Okay, and we just have these like is 0 constant 0. I call is black box constant with constant 0.
Okay.
And then we have our classical driver. Any quantum computation will have a sort of classical
Even this guy,
computer
he's
to tell it
getting
what to do.
linter errors too with the red squiggly lines. That's funny because that happens
think
to
he
me,
needs-
and I'm like,
I
I'm
think he
not
needs
wrong. You're the one that's
ESLint. Yeah.
yeah. Yeah, it
Or
looks like you have
prettier.
a syntax error in your code there. Just piping up from the audience. I can tell because of your red lines under your word.
Oh yeah.
Can you imagine?
You can
saying
see
that
the
to this
error.
guy?
Wait, you can see the error.
And so I ask for each
Oh.
of those 4.
Oh, I missed
what's
it.
going
Oh.
Yeah. If you go like a few seconds back, you can see it says like the name does not match.
Hold on, I want to see his error. And then I'll be done. I just want to see the error.
For identity, we run a CNOT gate with input as control, output as
Better
target,
the
remember
second
CNOT.
time.
and negation we use
Yeah.
CNOT and X. Okay, and we just have these like is 0 constant 0. I call is black box constant with constant 0. And then we have our classical
Does not
driver.
exist
Any
in the current context. Oh.
So I guess it's not defined.
Looks
It
like
just doesn't
a
exist.
looks like it's an import error or something.
Yeah,
Probably
probably.
line 4 is not coming through. It's not nice and bold. Maybe that's
No,
what
I think
he's-
line 4 means it's not being used. Like,
Yeah, it's not being used, so maybe that's like where this is constant 0. No, it's got to be coming from Dutch Oracle.qs. Namespace quantum.Dutch Oracle. I guess that's how you import in Q#.
I'm assuming. So then it has to be the other file, then the Dutch Oracle QS. You see at the top? See how there's
Yeah.
multiple files? So it has to be in the other file. Okay. Yeah, I understand Q#.
Mm-hmm.
This is easy.
Yeah, this is easy. I could do this in my
computation
sleep.
will have a sort of classical
All right,
computer
just run
to
the
tell it
program. I want
to
to see what
do.
happens when he runs it.
And so I ask for each of those. See
Okay, let's see.
the output. Is constant 0 constant? True. Constant 1 constant? True. Identity constant? False. Negation constant? False.
Oh.
So there you go. Yeah, we wrote the Dutch Oracle, ran it on a real quantum simulator. We saw that it worked out. Okay, the final demo of the day.
All right.
And then
hold
I'll
on.
let you get out
What's
of
the
here.
final demo? I just want to know what it is.
Here we go. This is called the IBM
This is
Quantum
kinda cool.
Experience. There is a real world
I know we're
quantum
on
computer that
over
IBM
time,
has
but I
built.
wanna see this.
It only has 5 qubits, but they just let you online just drag gates onto this quantum
Oh,
circuit diagram and run
that's
it on
beautiful.
a real quantum computer. So I thought it'd be pretty nifty
Amazing.
if we demonstrated entanglement, right, live for you on stage.
Okay,
Let's
I
see.
do want to see this.
So if you remember, the first thing we do is
H
you
for
drag a
Hadamard.
Hadamard gate onto 1 bit, and then we use the control NOT.
That's an
Oh, no.
entanglement.
Okay, so the way the quantum computers are constructed, you can only usually put CNOTs between certain bits, basically. It's just kind of, otherwise, it's just mechanically impossible. Let's see, can we do that? Nope. Okay. How about...
Gotta love a live demo. There we go.
Success. Okay.
Yeah.
We did it. Here's our, this is the CNOT gate. You can see varying representations of it. It's like the O+. And I say we'll run it on a
King
quantum
Man's
computer.
culture.
Oh, right, measurement gates. I forgot. You need to add the two measurement gates,
man.
obviously.
I'm totally missing chat. Chat's having a great
So
time.
we're measuring both of these qubits after entangling them. And what we expect is to see them predominantly being 0, 0, and 1, 1, right? Well, let's test it. We'll call it that. And because we can say the result from cache, but I want to do it live for you guys. So I'm going to run
Yes,
a
please.
new execution. And you can imagine right now, deep in an IBM research lab, nestled within a dilution refrigerator operating at slightly above absolute zero, we have real qubits being entangled and measured thousands of times for our entertainment.
That's
That's pretty cool. That's pretty cool. Okay.
And we're going to leave it
let's
there.
see.
And if you would like to learn more, the talk is called Quantum Computing for Computer Scientists, done by Microsoft Research. Only look at, of course, the verified profile, and we can get more. We skip this whole meaty middle part, so that's going to be something that you can dive into. But we did, I think, see some of the juicy parts, and like the top comment. This is aimed at computer scientists. Me, definitely not a computer. Finally a video for me. But we are computer scientists, so that doesn't apply to us. But I did think that was funny. But yeah, so I think that was really interesting. What are your big takeaways from that, Elias? Wrap it up.
It makes me think of computers in a different way, because now
Yes.
you have the theory of like it can be both zeros and ones, and then you can like transport them, like teleport them to different bits. And I think that's really cool. I find that fascinating.
I'm going to be absolutely intolerable the next computer science class. I'm going to be like, oh, it's a 0, 1, huh? Did you know about... Do you know about qubits?
Exactly.
Professor, how would this change if we started to think about in terms of qubits and maybe how superposition affects how it... And just
He's going to look at you like...
like, okay, dude, calm down. I don't know what you're talking about, but it sounds like you're making it up. And for all I know, I could be. But I think this is really cool. I would like to know how to mess with that IBM. Is that in the... Oh, not in the appendix.
I think it was if you go up to the video.
Oh.
And then just copy that link at the top.
Oh, yeah, I could do that. That's a good idea.
Or
have it here.
there might be a link here actually.
Who's the speaker? Andrew Helwer. Software engineers or networking, formal methods, distributed systems. Interesting. Yeah, I'm thinking about adding this guy on LinkedIn.
Let me see if I can find him.
Should I go find him on LinkedIn, like live? I don't know. That'd be kind of weird. But if I send this to him, I'm like looking up his LinkedIn live. Yeah, I don't know. I'm not going to do that. I'll look it up privately with my I'll look it up with my fake account. A chef at Florida International wants to connect with you. That's my fake account. Okay. Anyway, so let's go ahead and wrap it up, and we're going to go raid another channel, right? Is that what we're doing? Let's do it. Oh, so can people hear you, Jordan? Or is it just... Okay, they can't hear you. So Jordan asked how old I'm turning today, and I'm turning 28. Today's my birthday episode. Yay! April 10th is the best day to have a birthday. And because it's such a good day to have a birthday, we're going to go raid, as I understand it, another channel that has it's someone's birthday. Yeah, Chad, are you ready? Tell me it's both Brian's birthday and not his birthday. This is true because time zones and superposition.
Exactly.
Yeah, hit a 1 if you're ready to go raid. Hit a 0 if you want to just hang out and just talk about what Elias had for dinner for the next 30 minutes. Easy choice for me. Gotta know about that dinner. No, but anyway, thank you so much for coming on, Elias. And tell us about your show. Your show's on, was it Thursdays?
Yeah, I paused a little on the live streaming, but every new episode airs on Thursday.
Awesome.
Yeah.
Awesome. And
Oh,
how
yeah.
can we see that?
So
What do I?
oh yeah, facts. Find me in the Discord. My name is gonna be, I believe, Eli or Elias as my nickname. But my podcast is on all platforms. It's on Spotify, Apple Podcast, Beaker, Google Podcast. There's like 8 different platforms. So I'm everywhere.
Bro,
You
it's going
can't miss it.
crazy. What do I type
Can't
into
miss it.
YouTube to find you?
So I don't have any episodes up on YouTube. I just have the
But
first
you're on
one.
Spotify.
But I am on Spotify. Just search up the source code, and it's the very first one.
Okay.
Yeah.
All right. We're going to hit the raid button. I'm going to go look up the source code on Spotify. I suggest you do the same, but let's go ahead and go raid. Let's see what happens. Never done it before. First time ever. And if this is the last time for today, thank you all so much for coming. Galactic Bacon, source code, all my dogs in the chat. Thank you so much for coming and wishing me a happy birthday. All right. Now we're going to raid. I will see you all later. Bye-bye.
Oh, I actually think the chat is still. Oh, is it not?